have two talks, and the first speaker is Rozema from University of Vienna, and he'll tell us about the generation of polarization entangled photons with layered semiconductors. So please, Lee.
Okay, thank you. So I'd like to start by thanking the organizer for the opportunity to present this work here. The title of my talk is Generation of Polarization Entangled Photons. I tweaked it a little bit because a lot of what I'm saying is not specific to layered semiconductors, but rather to ultra-thin nonlinear media. But all of the work that I'll be presenting here was actually done with layered semiconductors. So before I start talking about the science, I just want to say a little bit about me. So my background is more in quantum optics. I work at the University of Vienna. I lead two research teams, one on quantum optics and quantum foundations, and this is really my background, so I'm really more of an optics guy than a condensed matter solid state guy. But recently, over the past few years, we've been trying to build up an effort in doing quantum nonlinear optics, and this is kind of how I got interested in these 2D materials and these layered semiconductors that I'll be talking to you about today. I also want to start by acknowledging all of the collaborators that went into this work. So about the first, I guess, 2/3 or half of the talk, depending on how fast I am, will be presenting the results of this paper that we were involved in, which was a lot of the sample fab and everything was done at Columbia University in the Jim Schuch group. But since then, we've carried on this work, and we're working with, in particular, Chiara Trovatello, who did her postdoc in Columbia, and now she's starting up her own group in Milan. And then we've also been starting to work with Andrea Marini as a theorist to help us describe and model what we're seeing in these materials. The PhD students who did most of the measurements here were Benjamin Brown and Josep Bajo. I think that's that. And with that, I'll get to the science. So almost everything I'll be talking about today is based on spontaneous parametric down conversion. This is a process that we've been using for, 30, 40 plus years, roughly, to produce entangled photons. But it's becoming more and more important, again, as we're seeing this demand for entangled photons for quantum technologies and so on. So I'm going to start by just recapping down conversion, and then I'll try to highlight what's different when we start doing down conversion in these ultra-thin materials. I'll show you how we can then kind of enhance these conversion efficiencies by introducing periodic polling, and then I'll talk a little bit about how we can generate entanglement in these systems and show you that using this polling we can then also preserve this entanglement. So as I said, the motivation for this work is really from the field of quantum technology. So I'm sure everyone's heard a lot about the quantum buzz, from funding agencies to popular press. We're all told we need to be doing quantum science to get funded and advanced technology and what have you. And quantum technology has a lot of different applications, from computation, imaging, and quantum communications, and it comes in many forms, from superconducting technologies to trapped ions. But for almost all of these technologies, photons are going to play an integral role, rather it be interconnects between solid-state systems or for quantum communications. And moreover, I would argue that all of these different applications require photon sources with different properties. So although we know how to make entangled photons using a bulk BBO crystal, this is not the end of the story, and we know that for a different application, we might need to tailor our entangled source to realize a source with different properties or in different contexts. For example, if your goal is to make a photonic quantum computer like PsiQuantum or Xanadu, then you really care about making small sources compact, integrated on a chip. And moreover, for this quantum computing idea, we need a lot of things to work together on a chip. We need photon sources, we need ultra-fast switches, we need single photon detectors, and we need a lot of them. So finding a single material platform that kind of simultaneously satisfies all of these properties is challenging. So it's going to require, at least at some level, some integration of different types of technologies onto a chip. Moreover, we might even need to cool everything down, because if we're stuck with nanowire detectors, superconducting detectors, we're going to need everything to work at low temperatures. So most of these experiments and most of these goals start with the process of spontaneous parametric down conversion. I'll just briefly say a few words about this. Just to make sure we're all on the same page. So down conversion is a second order nonlinear process. Most people are probably maybe more familiar with second harmonic generation, where we have an incoming light field at omega, which interacts with a nonlinear medium, generating a field at 2 omega. Down conversion is essentially the same process, just in reverse. We have one high energy photon at omega, which spontaneously down converts into 2 lower energy photons at omega over 2 in that case. Although the physics behind this process is the same, and it's described by this nonlinear tensor element, this is the kind of material parameter that tells us how strongly an incoming field can couple to our outgoing fields. Down conversion is a very inefficient process by definition. It's kind of spontaneous, and any attempt to turn up the field will work, but you kind of start leaving the regime of single photons. So in down conversion, we want to make things efficient. And in order to make things efficient, we obviously need to satisfy some physical constraints, the first being energy conservation, but also momentum conservation. So energy conservation is simple. The energy of the 2 down-converted photons just needs to add up to the pump photon. But we also need to satisfy momentum conservation. In nonlinear optics, we refer to this as phase matching, and I'll say more about this later. But the basic idea is, again, the momenta of the 2 down-converted photons has to add up to the momentum of the pump photon. And although this sounds simple, because this is now occurring in an optical medium, this can be difficult to satisfy in general. So it can be hard to find a material that's both nonlinear and is able to satisfy phase matching. But in the past, everyone has really focused on using long medium just because we're forced to. Because spontaneous parametric down conversion is inefficient, we need long crystals or long interaction times to enhance our nonlinearity. And if we don't satisfy phase matching, what happens, roughly speaking, is that as the pump fields propagate through the medium, the converted photons, the converted light fields get in and out of phase with the pump field. And if you plot the conversion efficiency versus propagation length, you find that it oscillates as a function of propagation length. So there's no net buildup of conversion efficiency. So this is, and in order to get rid of this effect, we need to introduce phase matching. And we're already starting to think about how to kind of work in this system when we want to use very, very thin nonlinear medium. So our first idea was, well, what happens if we just find a material that has a strong enough chi2 so that we can, just work in this regime? Can we find a material that has a strong enough chi2 that we can see photon pair production without needing phase matching? And this has a lot of interesting physics that kind of come along with it. Because phase matching imposes these energy restrictions, it turns out it restricts the energy of the down-converted photon, so it's difficult to generate entanglement in the energy basis. And one of our first ideas was, if we have a system which has essentially no phase matching, we should be able to generate very broadband spectral entanglement. And this is something we're still working towards, although we haven't seen it yet. But it got us looking into different materials and trying to find different materials that have strong enough chi2s. And the first material we were finally successful with in Vienna was this specific TMD, the 3R phase of MOS2 in particular. So this MOS2 has a non-optical nonlinearity that's about 10 to 100 times stronger than a standard bulk crystal like BBO. And in this 3R phase, you kind of avoid breaking the inversion. You do not have inversion symmetry as you add more layers. So you maintain the optical nonlinearity as you make your crystal larger. So this should allow us then to use materials that are on the order of a few hundred nanometers in order to see down conversion in this phase matching free regime. So we got a flake and we just tried it. So we started with different 3R flakes, but one of the first ones we had success with was a 400 nanometer flake. The experiment is relatively simple. We come in with a high energy pump photon at 780 nanometers. We pump our flake, and then we just couple the light into a fiber. So this red here is a multimode fiber in this case. Send it to a 50-50 beam splitter, and then we just look for timing correlations between the detection events of those two photons, and we see a very nice correlation peak. So So this already is interesting. This shows us that we can that these materials have strong enough chi2s for us to start looking at them as a serious contender for a subwavelength photon source. We then, of course, can do the typical measurements to verify that this is actually down conversion. We look at the power scaling. We see what we expect, the linear power scaling, which indicates down conversion. Or can indicate down conversion, you have to be careful, but we also look at then the coincidence to accidental ratio, this CAR. If you're not familiar with it, it's essentially the signal to noise. It's the ratio of your real coincidences to the background coincidences. And we see that we have very high values of CAR in the system, so we can see this signal to noise ratio of a few hundred from this crystal. So if we want to talk about how strong this nonlinearity is, we can then normalize by the length of the crystal and the pump power and compare to some of the standard BBO crystal. And we already find that with this flake, we have coincidence rates that are about 10 times brighter than the best sources based on BBO. Of course, although this is nice, it's not necessarily practical. Our coincidence rates are still on the order of a hertz, so it's something that we can measure, but it's not something you're going to make a practical photon source out of. So then we thought, and this is actually where Columbia came in. So from this point, then we can say, well, if we didn't try to use longer crystals, what's going to happen? Well, then we run into exactly this phase matching problem. So as we make the flake longer, we're not going to see any benefit to this. At some point, we'll actually destroy all of our down-converted light if we happen to be at one of these minima here. So the standard way to deal with this in nonlinear optics is to use phase matching, which forces these propagating fields to stay in phase. So essentially, the idea is you flip the sign of the chi2 on each of these oscillation points so that you see a net buildup of efficiency. In standard crystals like BBO or lithium niobate, we can do this using domain inversion by applying strong periodic electric fields. But how do you actually accomplish this in our platform where we have these very thin materials? And this is, again, this was where the Columbia collaborators came in, and they were already working on this for second harmonic generation. And they had this idea that why don't we start with our flake, and then we're going to carve it into these different rectangles. We then simply pick up each of these rectangles and stack them on top of each other, rotating it by 180 degrees every time. So we really mechanically introduce a periodic polling layer by layer. And here's an image of the results. So we can get the main limitation of this, so our flakes are still all exfoliated. So currently the main limitation is really just how big of a flake can we exfoliate. So far they've managed to stack up to six of these layers together. So then we can take these samples and do our down conversion again. And now what I'm plotting here is the enhancement to our coincidence rate as a function of the number of slabs. So we really just slide this sample transversely through the beam, measuring the coincidence rate from each layer. And we see with this particular sample an enhancement of about a factor of 20. So this is this was nice. We're very happy to see this. And this is essentially what we've published in this Nature Photonics paper I mentioned at the beginning. But what I've shown you so far just shows correlations. But are these photons entangled? And I just want to make this point because there's often confusion in this. Correlation in one basis does not imply entanglement. So just seeing this coincidence peak does not mean we have entangled photons. If we want to really verify entanglement, the temporal correlations we need to measure in a conjugate basis. For time, this would be energy. So then we would need to also verify that we have correlations in energy, which is something we're setting up to do. But in the meantime, we wanted to look at a different type of entanglement, which is also quite useful for a lot of quantum applications, namely polarization entanglement. So for this, I want to take a few minutes to explain how polarization behaves in down conversion in general. So what I've pulled out here is just a big table of the nonlinear tensor elements for different crystal symmetries that I got from Boyd's textbook. And if you want to see how polarization behaves, you can pick a specific row. So here I pulled out the non-zero tensor elements for BBO, which is a common nonlinear crystal, and highlighted these particular tensor elements. So what they tell you is how fields polarized along y and x kind of can couple to each other within this material. So for down conversion, if we were to pump, we would have the pump field is the white indice, the signal and idler fields are the yellow and red indices respectively. So this one that I've highlighted up here means that if we were to pump along the y direction, we should be able to generate a signal and an idler photon along the x direction. So you'll see that these first two tensor elements both have there's a YYY and the YXX. So what this means is if we pump along y, we can excite either the XX or the YY components, which means we should just directly be able to generate an entangled state where, writing it in the polarization notation, we should be able to make the state HH plus VV. Whereas if we pump along the x direction, we should be able to make HV minus VH. However, if you look in standard sources of entangled photons, this doesn't happen. In pretty much every entangled photon source paper you look at, they add these additional interferometers, multi-crystal geometries, or some other clever ideas to bring in polarization entanglement. So where does this entanglement go? It turns out the phase matching is exactly the problem. So in normal crystals, when we do phase matching, won't go into the details, but it's essentially polarization dependent. So we typically have to enhance conversion of just one of these tensor elements, which leads to these different classifications of nonlinear signals. So if you have type 0, we pump along H and we make HH, and so on. Type 2, we turn an H photon into an HV photon. So these aren't entangled. But now if we don't have phase matching, and we look at the non-zero tensor elements of our 3R MOS2, we find that we actually have the same 4 non-zero tensor elements. So again, this means we should be able to directly pump this crystal at 2 different polarization states and generate 2 different polarization entangled photon states. So this is what we've done. So we've pumped at different states, and we've built a quantum state tomography setup, and we can see we've generated the state HV plus VH. Rotate the pump polarization, we can make the state HH minus VV. We can also make something in between, so we can make a superposition of both of these entangled Bell states. And what I think is quite interesting, maybe it's not as flashy, but we can also turn off the entanglement. It turns out if you go through the math, if you pump with a circularly polarized pump beam, you can generate a separable state in the polarization degree of freedom, which is actually kind of interesting because it really means that the photons generated from all of these tensor elements have to coherently interfere in a very specific way to generate this state. So it shows again how pristine this system is. Right. So how does it behave with poling? So we've taken, again, these two different samples. So now we have a 4-stack and a 6-stack sample. We can measure that we see an enhancement in our rates through the poling. We actually see a larger enhancement from this particular 4-stack sample, and that's really just due to the fact that the thickness is a little different, and we have some Fabry-Perot resonances that hurt how the light couples out of the materials in our 6-stack. But in any case, we then do tomography for each of these different layers. This is kind of very noisy initial results, but I just got an email on Friday from my PhD student who just kind of retook this, taking care of some systematic data, but he hasn't replotted it yet. But we have 99% purity or higher from all of these poling periods. So even though we've introduced some phase matching, we still managed to keep everything coherent, so we have a very high quality entangled states. So what else can we do with this system? So this is a very flexible platform. One thing we started looking at was, it turns out we can also make different types of entangled states. So these Bell states are probably the states that you're most familiar with. But within the field of quantum information, there's a lot of other types of interesting state. One in particular is this noon state. So the noon state is a state where we take n photons and we create a superposition of all n of them polarized in one direction or all n of them polarized in the other direction. People like thinking about these for metrology purposes because if you apply a phase shift or a birefringence, you get a factor of n in the rate that the state is sensitive to the phase. And if we look at our TMD, it turns out these crystals directly generate noon states. So if we just pump our TMD and just look at the light coming out without separating the two modes, so in a single spatial mode, You can go through the math, and it turns out when you pump along H, now instead of generating the HH plus VV state, I can generate the 2,0 plus 0,2 state. So within this mode, it's essentially rewriting that state, but in the Fock basis. But what's interesting is if you look at what happens when you pump with a vertically polarized photon, we generate the state AHAV plus AVAH. If I write that state in a different basis, so I'm just doing a linear transformation, I'm really just tilting my head, and instead of looking at the state in the HV basis, I'm looking at the plus minus 45 degree basis. It turns out that this state is the 2,0 plus 0,2 state in the polarization basis. In the plus minus 45 degree basis. And what's interesting is that in order for this to work, it requires, in addition to that all of these tensor elements contribute coherently, it also requires that these two photons undergo two-photon interference. So this is essentially what people in quantum optics call a polarization Hongo-Mandel dip. And the question is then, can we see this effect using our photons? And what also, the other thing I wanted to say is this isn't specific to that basis, and this is where I think there might be some interesting applications, is you can actually generate the state for any pump polarization. So any linear pump polarization you make creates a noon state in a rotated basis, which just follows the incoming pump polarization. So we have some preliminary measurements where we've implemented a different type of tomography setup to characterize this. So this is the density matrices we've reconstructed in the 2,0 in the Fock basis. So for the one state, for the state above, you see we have HH plus VV, so 2,0 and 0,2. And down here, almost all of the weight is in this state. This doesn't directly tell you about the Hongo-Mandel visibility. But to show this, I'm happy to discuss these plots in the break. What we can do is look at how these states, try to picture how these states look on the block or the Poincare sphere. So this is a Wigner function of these density matrices transformed on the Poincare sphere. Roughly, it's the probability to find two photons polarized at any point. And the fact that we see these high contrast fringes shows that we have essentially high contrast Hongo-Mandel visibility. And extracting it from our measurements, we have Hongo-Mandel visibilities of about 98%. We can also directly measure this if you prefer. So we take our TMD, we pump it to generate the state HV. So this is this diagonally polarized noon state. And then we just rotate a half wave plate and look at our coincidence rate. So now we're seeing just directly these coincidence counts oscillate. So although we're starting with all of our light at HV, when you rotate our polarization measurement, at this point we have almost perfect Hongo-Mandel interference between these two photons. So this is interesting, and we're planning to continue studying these states in this context. I just wanted to briefly say we're also interested in kind of making these sources a little bit more practical, so doing things like integrating them into waveguides and so on. And one place we think we might have a particular advantage is when we look at temperature performance. So because we don't have to satisfy phase matching, so normally when you have a phase matched crystal, it depends very much on the length of the crystal. So as you cool or change the temperature of the crystal, you see your photon production rate varies quite sensitively with the photons. So you change it by a degree and your photon rate can drop. But in our source, we see almost constant behavior, almost identical behavior between operation at room temperature and 6 Kelvin. So here I'm just plotting the coincidence rate versus pump power, and there's almost no difference between the two situations. In fact, we actually see a slight enhancement when we look at this. This is, again, the measure of signal to noise, so the measure of real coincidences to accidental statistical flukes. And we see that we actually have an enhanced signal to noise in our coincidences at 6 Kelvin compared to room temperature. So finally, we're interested in scaling these things up, but we'd also like to go down to a monolayer. We think the nonlinearities in this system is big enough that we might be able to get there. And actually, one of the reasons we started looking at this temperature tuning was to reach that direction, because we can kind of shift the PL in and out of our detection window. And there was a paper that actually just came out it was on the archive this summer, but it was just published in Science Advances last week, where they showed really photon pair production from a different 2D material. So it's something that's within reach. And once you get to the monolayer region, I think there's a lot of interesting physics that we can do. There's proposals for exciton enhancement, potentially things like generating entanglement between photons and excitons and so on. But that's all future goals. So with that, I'll conclude my talk. I hope I've shown you that this 3R-MOS2, and in particular these, in general, these thin materials have a lot of potential advantages for generating photon sources. I've shown you different ways we can make entangled states and some initial work on temperature dependence, and we have a lot of ideas on where we can go from here. So with that, I'll stop talking and happy to take any questions.
All right, thank you, Lee. And we have time for questions or comments from the audience.
Thank you very much. Very impressive. I just wanted to ask more like a technical question. In your last slides, you were showing the the power that you're putting, which is like up to 8 watts.
Oh no, no. This is up to. This is 8 milliwatts. So there's.
It's a micro.
Micro. Yeah, exactly.
Okay.
So
I was just wondering because I thought.
No, that would destroy everything.
But actually, then this is the question: is that okay? Then, how much can you like? What do you expect for the rate, the maximum rate that you can produce?
Yeah. So this is where we have to. So I think with the polling, if we extend it out by another 10 layers or something like that, we should be able to see rates on the order of 100 to 1,000 hertz or so. We're already seeing absolute rates of 10 to 100 hertz. So with another 10-ish layers of polling, we can enhance the rates. But we don't know how the polarization will be preserved in these as we go there. So this is something we're still interested in studying.
Okay, thank you.
All right, I think we had here.
Thanks for the talk. My question was mainly like on this idea of like integrating, because how would you be able to poll the material in a way that you have it along a waveguide rather than like normal to a substrate?
Yeah, so we have different ideas, but one idea is to kind of directly deposit the material on the facet of a waveguide, and then pump it with a pump with a free space pump laser, and then generate directly into the waveguide mode. These are all things we're exploring. We're also thinking about doing this on a fiber tip to put it directly in fiber, where then we can filter at the pump. But yeah, it's all work in progress.
All right, Anton, please.
Thanks, Lee. Nice talk. I was wondering if you pump harder your system, eventually you start getting higher photon contributions.
Yeah.
And so those purities that you showed us, how does it, compromise the brightness and?
Yeah. So the purity will reduce. So I mean, it's kind of in. Where do I have a plot of it? In one of these signal to noise ratio plots. So. Somewhere way back here, or not. Oh yeah. So we haven't done this directly with the entanglement yet. This is again data we're taking, but we see so our purities are currently measured with these signal to noise rates of about 10 to 50. So we're in this regime. So if we pump harder, we do start to reduce things, but it's not a huge reduction. But the other thing I should say is these measurements are all done with a lot. Well, so a lot of this degradation comes from the fact that we have some tails from the photoluminescence in our detection bandwidth. So by pumping at different wavelengths or by temperature tuning the material, we're playing around with shifting the PL out of our detection bandwidth so that we could then, I mean, you always see the scaling, but if you can shift it out, then you can kind of, shift the whole curve up. So, but this is kind of standard for any down conversion experiment. Even with a BBO crystal, you see the same behavior.
Yeah, absolutely. And eventually, at some point, it will become a stimulated process, right? And where is the threshold for the stimulation roughly on that
I don't
scale?
know
Is it
here. It's
100 milliwatts or maybe more or less? Do you have an
no,
idea?
it would be much, much higher. So normally, even with down conversion, you need to put it in a cavity in order to reach the stimulated threshold. So in our setup where it's just a bulk crystal, I don't know. The material will be destroyed we need to, before we reach that.
That's a quick question. So in the noon states, as far as I understand, it's only possible for the 2 photons, right? You cannot create n equal 4 or 5 unless you multiplex or something like that.
So you don't make an n equals 4 or 5 state, but what you can do is the inverse of this, actually. So here at the top, I say when I pump with V, I make an HV state. This HV state is already interesting for quantum metrology. It's not the noon state, but it has the same sensitivity features. So if I, instead of making 1,1 in the HV basis, I make the state 2,2, I still have my super sensitivity scaling. So I could make that state, and then the argument applies in reverse. So you still make this interesting metrological state, but it's not a noon state. If you think about these Wigner spheres, these Wigner plots, you still have a single band around the sphere, and it just gets narrower. And if you measure birefringence, you're essentially sensitive to the slope of this Wigner function. So you can still get this sensitivity enhancement.
Thanks, very cool.
All right, I think I saw one last question. Yeah, please there.
Thank you for your talk. So instead of stacking the new layers, what about just putting in a resonator? Are there arguments against it?
Just the power. There's no reason not to. We've also thought about putting these things in cavities, but it's just different physics going to it, let's say. So you can then essentially you enhance the emission into that mode. You would narrow the spectral emission. So in our case, we have very broad emission because our phase matching is so light. So if you start to put it in a cavity, you can get narrow spectral emission. And you would enhance, let's say, the brightness per nanometer of bandwidth in that case. Whereas here, we're enhancing the brightness just over a very broad bandwidth. So could also work.
Thank you.
But,
All right, so with that, I think we'll thank the speaker again. So thanks a lot.
thank you.